Great. Thanks a lot for inviting me to give this talk. Today, I'm going to talk about some recent work done in my group in the problem of applying deep generative models for molecular design. I'm going to start with some by giving thanks to my collaborators. These are some of my PhD students, Austin Tripp, Eric Dagsberger, and John Bradshaw. The work that I'm going to present was done by these students, and also with some collaboration from amazing researchers such as Matt Kursner, Brooks Page, and Marwin Segler. So to motivate the work that I'm going to present, I'm going to focus on some problems that appear commonly across science and engineering. These are problems in which we have to optimize an expensive black box objective function over a high-dimensional structured input space. And a few examples of those problems appear in drug and material design. In drug design, the black box function may receive as input a description of the molecular component forming the drug, and the output is going to be some estimate of the efficacy of that drug for treating a particular disease. Another example is in the design of organic photovoltaics. The black box objective function may receive as input a description, a molecular description of some material used to build the photovoltaic panel, and the output is going to be some estimate of the power conversion efficiency of the resulting material. Solving this type of optimization problems is challenging because evaluating the molecular properties is slow and expensive. If we want to assess the quality of a particular drug molecule, this may involve running expensive experiments. And to estimate the power conversion efficiency of an organic photovoltaic, maybe we have to run expensive simulations. So this means that evaluating our black box objective functions is going to be expensive. And another problem is that the space of molecular graphs is huge and with complex constraints. Identifying the few molecules that have relevant properties in this huge space is going to be difficult and time-consuming. And we are also interested in not finding arbitrary molecules, but finding molecules that are similar to the real-world ones. We want molecules that are easy to synthesize in practice, or molecules that are stable and are not going to degrade quickly. So how can we solve these problems? A promising approach appeared recently, and the idea is to use a deep generative model that can be trained on data corresponding to descriptions of existing molecules. This model can map then molecules into some continuous latent space. This could be a variation autoencoder model that encodes the molecules into the continuous latent space, and it can decode the molecules back into the original molecular representation. We can then combine this generative model with a predictor that maps points in the latent space to the properties of the corresponding molecules that are obtained when we decode those points. Molecular optimization can then be done in the continuous latent representation. We can look at the estimate of the property of the molecule for a point in latent space, and then follow the gradient of the predictor for the property to move into other areas of latent space that are going to decode into molecules with improved properties. This sounds like an exciting approach. It allows us to solve some of the challenges of this type of optimization problems. We are now working in a continuous latent space, which is going to be of a low dimensionality, so we avoid working with a structured high-dimensional input from the original problem. We can also use existing efficient optimization methods in latent space, such as Bayesian optimization methods, that will allow us to collect the data efficiently to find new molecules with improved properties. Because we're using a generative model to decode points in latent space, we have that the decoded points will exhibit similar properties and patterns to those molecules found in the training set. This means that our generated molecules are likely to be realistic and present similar properties as those of the existing ones. So this is great. This is a promising approach, but this approach has also some limitations. And in this talk, I'm going to describe new contributions that will address some of the existing limitations of this type of models. The first part of the talk is going to focus on weighted retraining, which is a method that has already been accepted for presentation here at NeurIPS. And here I'm going to just give a brief description of this method. Here we address some of the limitations of current methods for the optimization in the latent space of deep generative models. We call these methods that perform optimization in latent space LSO, latent space optimization. So previous methods, they worked by training this deep generative model on existing data, and then the model was used for optimization in the latent space. But the model was not really retrained after collecting new data. This means that if our deep generative model has been trained on some training data that contains some promising values, but those promising data points are far away from the optimal ones, our trained model may not be able to generate improved data points or find the optimum of the optimization problem as shown here with this yellow star. So we have this model that has been trained on these observed data points shown as circles. They overlap slightly with this promising region in green, which has good data points, and the optimum one is shown in yellow. But with our deep generative model, we can decode into this area shown with this dashed line, but we cannot really access this other region that contains the global optimum. So in this sense, our methods won't be able to find an optimum which is far away from the training data if we don't retrain them on newly collected data. However, even if the model is retrained, the new data points may be only a few ones, and they will have a diminishing effect when we are training these models on large amounts of data collected initially. So if we have a very large initial training set, we want to do optimization starting from that point and we want to collect data for a few new data points. The new data points that we collect will have a diminishing effect. And it means that if we retrain our model, maybe the effect of that retraining is going to be very small, and we won't be able to notice that. So in this work, we address these problems by actually retraining the deep generative model, as we mentioned before, to avoid the problem one. And then to avoid the diminishing effect of the newly collected data, we are going to weight the data so that we give more weight to those data points that have better or improved objective values. We call this method weighted retraining, and it works as follows. We are going to retrain our deep generative models now after collecting new data, for example, after collecting new 50 data points. And then we are going to use weights to give a higher contribution in our objective value to those data points with better objective. So we can write our objective value in terms of a sum over the data points that we have in our training set, and we have now a weight associated to each data point. This could be, for example, the objective value could be the elbow, and you could also decompose it in this way. The weights are given by this expression. It's 1 over k, which is a hyperparameter, times the number of data points, plus the rank of the data point in the training set according to the objective value. So if the data point is the best one in the training set, the rank is going to be 1. And if the data point is the worst one in the data set, the rank is going to be n. And then we subtract 1. So this weighting function has the following property. If we set our hyperparameter k to infinity, this means that the weighting is uniform across data points, and then this weighting function is not having any effect on the training of our model. And if k is small, in particular close to 0 or equal to 0, all the weight is placed on the single data point on the training set with highest value. And for intermediate values of k that are slightly larger than 0, but not very large, we will have that those data points with better objective values receive a higher weight in the training. And this is illustrated in this plot. We have here objective values for different data points, which correspond to molecules from the zinc data set. This is about 200,000 molecules or so. And we plot the objective values. And here we see that we have quite a wide range of objective values in the training data. The training data is shown in blue. This is the unweighted training data. When k is large, like 100 in this case, the weighted data is very close to the original unweighted data. And as we reduce the value of k and we get closer to 0, we have that those data points with better objective values receive higher weights. And we see that the histogram of the data is now skewed towards those data points with improved objective values. And if we actually fix the k to 0, we will have a delta function here placed on the best single data point. Good. So we can then tune our weighting by choosing k. We see that our weighting also depends on the number of data points, but the good news is that in general, if the product of k times n is large, then the weighting distribution is going to be independent of k of the number of data points n, and it's going to depend only on our hyperparameter k. This is illustrated in this plot. We have curves of the weighting functions. This is the cumulative weight fraction as a function of the data fraction that we consider at each point. We see that when k is relatively large, in this case is closer to 1, the weighting function is close to the identity. So it means that the weighting is similar to uniform. And as k gets closer to 0, in this case, k is 10 to the minus 2, the weighting is significant for those data points that have better objective values. So the data fraction here corresponds to the fraction of data as ordered according to the objective value. And we see that the data points that have better objective values, which appear at the beginning, will have higher weights when k is closer to 0. What is interesting is that these weighting curves, they are independent of the number of data points. And this happens because the product of n and k is relatively large. So independently of the number of data points n, we can then focus just on choosing some value of k that performs well in practice. And typically, we will choose values of k equal to 10 to the minus 3, and we saw that this works well in practice. So by using this weighting function, we are actually given more weight to those data points with improved objective values. For example, here, the pink data point here has a larger weight when we train our model. It means that we will have a larger fraction of the latent space that is going to map to points that are similar to this pink point. And this means that by retraining and collecting more data, we are actually allowing our model to focus more on those regions of the input space that have better objective values. And this will allow us to find the global optimum in this cartoon description of the program. So with our approach, a larger fraction of the latent space maps into regions of the input space with high objective values. So how does this work in practice? We evaluated it on a simple problem. This is the problem of a 2D shape area maximization. We have a data set of square shapes, and we want to generate a square shape now with the largest possible area. And this will be a square that just fits the whole of the image. We have an initial training set with about 250,000 of square shapes. The objective value is the area of the square, and we want to generate the square with the largest area. We do search in a latent space of 5 dimensions, and we're going to retrain our deep generative model every 50 iterations. We're going to collect data for 500 steps. So we will be retraining 10 times. And I show here the distribution of objective values in the training data. We see that there are many shapes with a low area, and then a few ones have larger area. This is in gray here, the distribution of objective values for the data generated from the original deep generative model without weighting the data. And we see that has a similar shape as the distribution on the training data. These are, by the way, violin plots. So they plot the distribution along the y-axis. We then consider different weights of weighting, different degrees of weighting. The original variation autoencoder model, and we see that as we increase the amount of weighting and the k is equal to 10 to the minus 3, we have that the model generates more data points with improved objective values when we compare it with the pink curve. And after the optimization process, we show the samples generated by the model in blue. This represents the objective, the sample distribution of samples, distribution of objective values for the samples generated from the model after collecting 500 function evaluations. And we see that when k is 10 to the minus 3, we are weighting the data to favor those data points with improved objective values. We obtain much better samples. This is shown in this plot that shows the best square shape generated as a function of the number of evaluations. And we see that when we apply weighted retraining, we obtain much better results than when we don't do weighting or retraining. We tested this also in the problem of designing new molecules with a focus on optimizing this log P score, which is related to the solubility of the molecules. We start with an initial data set with about 250,000 molecules from the Zinc database. We are using, again, a weighted retraining with k equal to minus 10 to the minus 3. And we use a junction tree variation autoencoder with sparse GPs for the optimization. We see that weighted retraining significantly produces significant gains when we compare it to not weighting the training data and not retraining. So to conclude, in this first part of the talk, we have seen weighted retraining, which is an approach for latent space optimization that results in latent spaces that are highly useful for optimization. We apply this to different problems, and we see that weighted retraining improves the data efficiency and the final performance, and it's actually a very simple and easy to implement technique. So this is the first part of the talk. The second part of the talk addresses another limitation of this approach based on using deep generative models for molecule optimization. And here we are going to describe a new deep generative model that is going to generate molecules via chemical reactions so that the model tells us how to synthesize the molecules in practice. Here, we are aiming to address a limitation of these deep generative models of molecules, that they will typically generate just molecular graphs, and they will not tell you how to synthesize the generated molecules in practice. Ideally, what we want is a deep generative model that will generate molecules via chemical reactions, so that you know how to synthesize the final product molecule in terms of some initial reactants. The advantage of this approach is that the generated molecules are more likely to be synthesizable in practice because they are actually generated in the same way that you would produce them in the real world. The model gives you synthesis information right away, which can be useful. And because the molecules are now generated via chemical reactions, they will exhibit more realistic properties. For example, they are more likely to be stable and not reactive, and so on. And they will be also easier to synthesize in practice. So how do we do this? What we propose is a multi-step. What we propose is to focus on the description of multi-step reactions as a directed acyclic graph. And this is illustrated here. We have a directed acyclic graph with some nodes that correspond to building blocks or materials, or starting materials that are already available, and we have some intermediate nodes, intermediate product nodes that represent the intermediate steps of the chemical reaction. And at the end, we will have some final product. This shows the synthetic route for paracetamol, and we're going to describe this in terms of this directed acyclic graph. And we want our model to generate graphs of this type. Our model is going to generate directed acyclic graphs of molecular graphs because each node in this graph is going to be a molecular graph on its own. So since we are generating DAGS of molecular graphs, we abbreviate these as DOGs, and we call our model DOG. So we are going to be generating this type of graphs, and we are going to use as training data about 72,000 synthesis DAGs or DOGs from the USPTO dataset. This is a publicly available data set of chemical reaction data. So how do we generate these synthesis DAGs? We generate them sequentially. We break them into their constituent parts. We have building block nodes, and we have intermediate product nodes, and some final product node. And we start to generate them sequentially as follows, following some actions. We start by creating an initial building block node, which is initially empty, and then we choose what molecular graph to include in that building block. This would be an initial reactant for our synthesis route. We then add another building block as this one. We decide its content, and then we add an intermediate product node and choose to connect it to the first building block that we generated, and then to the second, and then we stop. Once we stop, we can use a method for reaction prediction that will fill in the content of this intermediate product node. This could be, for example, the molecular transformer, which is a state-of-the-art method for reaction prediction. The next step could be to add another building block, as shown here, its content, and then some intermediate product node connected to other nodes that already exist in the graph, and then we fill in its content. And then we will add another building block, its content, and then another intermediate node. And actually, we say this is the last intermediate node in our reaction, which means that it's the final product. And we connect it to the previous nodes that have no descendants in the graph, which would be this one here and this other one. Good. So in practice, we implement this using an autoregressive model that selects the next action to apply as a function of the previous ones. This is implemented in practice using a recurrent neural network that conditions on past actions. The hidden state of this recurrent neural network encodes the information from all the previous actions taken. And we're going to feed into this recurrent neural network information about the current state of the synthesis DAG using the embeddings generated by graph neural networks. The whole approach is described here. We have our recurrent neural network, which may receive as input maybe some continuous latent representation of the synthesis DAG or not, if depending on whether we use an autoencoder model or just an autoregressive generative model. The recurrent neural network receives as input the embedding of the previous action. Then there is like a neural network that determines the next action to apply, in this case, to choose a particular building block. The neural network also receives information about the current state of the generation process. So once we have chosen a particular building block, then the next action is to determine if we add another building block or an intermediate product node. We choose another building block. We choose the content of that building block. We mask out other building blocks that were generated before and cannot be added again. We then generate an intermediate product node. And then we determine to which existing building blocks or nodes in the graph we connect it to, and so on. So our model is just for the actions that involve the construction of the nodes in the graph, and the content of the product nodes, as I mentioned before, is generated by calling the molecular transformer, which is trained independently. So with this approach, we have two ways to generate data. We can just consider our model DOG for generating molecules in an autoregressive way. In this case, we don't condition to a latent space, and we call this method DOG-gen. Interestingly, this method can also be used for molecule optimization using techniques such as the cross-entropy method. And the idea is that you will be training your model on your existing data set. You show here the objective values in the original training data in light green, and the objective values for the generated molecules in with a discontinuous line. And we see that we can then look at the objective values of the best molecules generated by the model, and then retrain on those, and generate molecules again. And then we repeat the process. We focus on the best molecules generated by the model. We throw away the other ones, retrain, and then repeat the whole process until we obtain some model that is now generating improved molecules with objectives better than those found in the training set. Another approach is to combine this model with some encoder, and then we have a variation autoencoder model that maps synthesis trees into some continuous latent space. And then we can decode those trees back with our generative model. When we do that, we can actually have a continuous representation of the synthesis graphs. And this is shown here, how we can explore that latent space. We can have this data point in the training data. It's a synthesis graph. And we can then map it into latent space and then move slightly in latent space and decode to similar graphs. And we see here that we obtain another graph which uses another intermediate product here. And the output is another molecule that is similar to the original one, but slightly different. If we move again in latent space by a small amount, here we are doing a random walk in latent space, we obtain another similar synthesis DAG. And this is another one. And another one. Cool. So we can then test how our model is, the quality of our model in the generation of molecules. And here we just feed our model to the training data, and then we sample from the model and we look at metrics of the generated molecules. In particular, we look at the Freshet ChemNet distance, which is similar to the inception score used to evaluate the quality of GANs generating images. Here we do something similar, but we focus on the quality of the molecules generated. Here lower is better, and we see that DOG-GEN, our autoregressive model, generates molecules with similar metrics to some of the best existing models in the literature. The other metric that we look at is the quality filters from the Whack-A-Mole benchmark, and here higher is better, and this represents the fraction of the generated molecules that pass those quality filters that assess how stable or non-reactant are the molecules that we generate. We see that again, we are able to generate molecules with similar metrics as those of previous baselines that are actually more flexible because they are not restricted to generate molecules that are synthesizable. So this is quite interesting that even though we have a more constrained models, we can generate molecules with a similar quality as other techniques. We look at the quality in terms of molecular optimization. Again, we focus on some problems from the Whack-A-Mole benchmark tool. And we see that we obtain similar results as previous baselines, even though we are constrained to generate molecules that are synthesizable, while the other models are not constrained and they are more flexible and in principle should be able to obtain higher scores. So finally, we look at how good are the molecules that we obtain through the optimization process. Here, the optimization process is done, as I mentioned before, using this cross-entropy method, in which we train our model on the training data, and then we sample from the model. We take the best generated molecules and retrain the model on those, and we iterate. We look at the metrics of the top molecules in each of the different optimization problems that I mentioned before. We look at the fraction of top 100 molecules that are synthesizable. And we see that the DOG generates a larger fraction of molecules that are synthesizable when during the optimization process as compared to other baselines, which generate optimal molecules that are less likely to be synthesizable. And we look also at the fraction of molecules that pass the quality filters that I mentioned before, the fraction of optimized molecules that pass the quality filters. And we see that we obtain a larger fraction of molecules when using our model, which means that our model generates molecules that are more stable or less reactive. So to conclude, I have described here DOG, which is a deep generative model of molecules that works via chemical reactions, and it generates synthesizable molecules up front. It works by generating molecular synthesis DAGS or DOGs in a serial way, and it obtains competitive results when doing molecule generation and optimization as previous baselines, with the advantage that it generates molecules that are more stable and have a higher degree of synthesizability. Oh, sorry, I forgot to mention. So when we evaluate the synthesizability of the molecules, we do this by running a retrosynthesis software that is trying to find some synthetic route that actually generates the target molecules. So this is an independent approach that is different from our model. Good, so that's all. Thanks for your attention, and I will be happy to answer any questions.